Okay, welcome to System Devices 1, Lecture 6A, CPU, where we start to look at the processor, the central processing unit, our simple CPU version 1A, and how we can optimize it, how we can improve it to perform the types of programming tasks we want to do. So with our simple CPU version 1A, we do have a functioning computer. We can program it to perform certain tasks, but we really need to add some additional features to make it more practical. One of the main ones is subroutines. We can implement those using self-modifying code, a wheel, a jump, but that's not really a practical solution. Self-modifying code is never a good idea. So we need to add some hardware, some mechanism to allow the processor to call subroutines, to call functions, to reuse software blocks to help improve our memory efficiency. We also need to consider the types of data we'll be processing. The simple CPU is an 8-bit machine, and for most of the stuff we've been doing, that's been fine. Representing numbers from 0 to 255 gave us a sufficient range for most tasks. But as soon as you start to look at real-world applications, that number range is just too small. For example, image processing, where you've got thousands of pixels in an image, you need to identify them. You need to represent larger numbers. Also, we saw in the Hello World program, accessing arrays is difficult using the simple CPU version 1A. So we need a way of indexing those data types. We need a way of indirect memory accesses. And finally, memory capacity. So 256 storage locations is quite small. You can only really implement simple programs with that one. We need more memory or a method of expanding memory. So I give you the simple CPU version 1D, the new and improved processor. Now looking at this schematic, you may spot some common elements. So you can see down the bottom here, we've got our ALU, we've got some control logic, we've got instruction register, our data multiplexer, program counter, address multiplexer, and our general purpose registers. But equally, you can see some things have changed. Improvement number 1, more memory. You always need more memory. It's surprising how quickly it runs out. And we saw for the LCD version of Hello World, it took a couple of hundred instructions to actually print Hello World to the screen. And if you've only got 256 instructions, that doesn't leave you an awful lot of room for other functionality. So for the simple CPU version 1D, we're going to increase its memory size to 4K, so 4096 storage locations. But obviously this will have an impact on the computer's hardware. So what architectural features do we need to change inside our system to allow it to address 4000 memory locations? That is, how will it affect the communication links, the various hardware elements in our system, so the registers and multiplexers and other logic, and perhaps more importantly, how will it affect the format of the instruction, as we're limited to 16-bit storage. So the first modification you may have spotted is the address multiplexer. You'll see it has an additional input and the number has changed there from 8 to a 12. So if you go through your base 2 numbers, you will identify that to address 4096 storage locations, you will need a 12-bit number, a 12-bit bus. So the address bus has been increased in size from 8 bits to 12 bits, obviously address bits 0 to 11. The address multiplexer still has the program counter, the instruction register coming in, but it also has an additional register coming in here. This will allow us to do indirect addressing, allow us to access arrays, which you'll see later. So perhaps not unexpectedly, the address bus will need to increase because we've increased the size of the memory, so we need a bigger address bus to address that memory. But maybe lost in the detail there is the effect on the instructions. So here you can see our original load instruction, so we had our opcode, some bits unused, and an 8-bit address to address the simple CPU version 1A's 256 storage locations. Increasing the memory size obviously means that we need to store a 12-bit address in the instruction, and so we can simply use these unused bits to create that 12-bit value. So from this you can see why I chose a 4K memory size, because that is the biggest address I can fit within a 16-bit instruction, because I need 4 bits for the opcode. If I wanted to move to a 64K address space, I'd need 16 bits to represent that address, and obviously that wouldn't leave any room for the opcode. I'd have to move to a 20-bit instruction format, 4-bit opcode and a 16-bit address, which would mean that the new processor wasn't backwards compatible. Obviously I can run on the simple CPU version 1D the old simple CPU version 1A's code, because the structure of the instruction is compatible. Finally, always remember even small modifications can lead to a significant increase in hardware complexity. So you can see here going to a 12-bit, but going to a 12-bit address bus means we've got a 30% increase in our hardware requirements for the address multiplexer. Again, you can see this in terms of the program counter. Obviously we have to increase the program counter size from 8 bits to 12 bits now to allow us to use this memory. And again, that all comes with a hardware cost. So generally speaking, if you look at a processor and think, why did they do that? It's normally because they had to make a compromise. They decided it wasn't worth implementing a particular feature because it would increase the hardware, making the processor more expensive and less cost effective. As well as improving external memory, the simple CPU version 1D's internal memory is also expanded. So rather than having a single general purpose data register, the accumulator, we now move to a register file, a bank of internal registers. So within our register file, this component symbol here, we have 4 general purpose registers. And in addition to increasing the number of storage locations, I've also increased the size of these storage locations, moving them from 8 bits to 16 bits, allowing us to store larger values. So if we zoom into the internals of this register file, we can see 4 16-bit registers, register A, B, C and D. And to select which register we'll be reading, we have an output multiplexer and we also have an input decoder. So in the instruction, we now need to specify which register we'll be writing to and which register we'll be reading, as it's no longer implicit. And that was an advantage for the accumulator-based architecture. You didn't need to define within the instruction where one of the operands was coming from and where the result was going, because it was always the accumulator. Now we have 4 general purpose registers, so now we need some way of identifying the source and destinations of our instructions. You will also notice there's an additional 4-way multiplexer down the bottom here, and we use that for additional addressing modes that we'll be looking at later. Okay, so as I pointed out, we will need to identify which register we're reading and writing, so how will this affect the instruction format? As always, the instruction defines the opcode and the operands, so the operands need to be specified somewhere in the instruction. So we could use some of the bits within the 4-bit field not used by the simple CPU version 1A, as shown here. So we could define a 2-bit bit field, which defines which register we'll be reading and writing to. So a 2-operand format. So we've got our opcode specifying we're doing the add. We have 2 bits specifying which of the 4 registers we will be reading and writing to. And we could specify a 10-bit immediate value if we wanted to. Or we could decide to go to a 3-operand format instruction. So again, here we have our opcode. Now we have 2 bits to define which register we're reading, and we can define a separate register, a different register, to where the result will be stored, and use an 8-bit immediate value. And these both have some advantages and disadvantages, but it's a choice for the designer to make. As you may have spotted, going to a register file has some problems for our load instruction, as we have already used those spare 4 bits for our address. So we have no spare bit fields within the 16-bit instruction to specify the destination of our load. In these cases, it's implicit, so the load instruction can only store the data it's read from memory to register RA. It can't store it to any of the other registers. Again, you'll find that quite common in different processor instruction sets. There's limitations sometimes for your source and destination operands. Obviously, one way around that one would be to move to a 18-bit instruction, add an additional 2 bits to specify the destination, but obviously that would increase the size of our memory. Again, as previously mentioned, you always get this ripple effect happening. So you make one small modification to the hardware somewhere and that will impact elsewhere. So previously, when we only had one general purpose register, when we did the 0 test, it had to be on that register. It had to be on the accumulator. But now we've got a register file. When we do a 0 test of jump if 0, jump if not 0, what register are we testing? Now we could explicitly define that within the jump instruction. So test register RA, test register RB, etc. But again, that would increase the size of the instruction. So one way around that one is to have an additional register that remembers the outcome of the last arithmetic or logical operation. So we can use a register within the processor to store these flags. In the previous processor, we only tested the 0 flag. It was the result of the last arithmetic operation 0. But to help structure our software, we can now increase the number of status flags that are stored in our system. So within the simple CPU version 1D, we actually have a 5-bit status register where we can store information about did the last arithmetic or logical operation produce a 0, a carry, an overflow for signed values, did it generate a positive or a negative result. And we can have conditional jump instructions that test these particular conditions. Okay, improvement number 2, data types. As previously mentioned in the register file, we've moved to a 16-bit general purpose register. So that allows us to increase the size of numbers we can represent from 8-bit values. So for the simple CPU version 1A, unsigned was 0 to 255 or signed minus 128 to positive 127 to a 16-bit data type. And we do need to represent these larger numbers. If you look at the image processing example we'll be doing in the labs, there we'll be processing RGB images and they represent the various pixel colors using 8-bit values. So if you need to process those values, you could have to add up 3 255s, which gives you the result 765, which wouldn't fit within the 8-bit accumulator. So moving to a 16-bit internal storage allows us to represent obviously a lot larger values. So unsigned 0 to 64K, and obviously signed minus 32K to positive 32K. Again, this ripples through, so if we increase our internal storage to 16 bits, what else do we need to increase? Well, it's the whole of the data processing chain at the bottom here. So the ALU, our ripple adders, our bitwise ANDs, or whatever functional units now need to be 16 bits. Routing those values around the processor increases the size of the bus. So we move from 8-bit internal communication buses to 16-bit buses, which again all takes space within the FPGA within the silicon. So again, a significant increase in hardware costs. Now here we have a good example where we get disconnects between our hardware architecture and our instruction set. So we can make changes to our hardware architecture without realizing we've introduced some problems in the instructions that will be using it. As this question here now states, can you actually load one of our 16-bit registers with a value, with a 16-bit value? So if you have a look at this move instruction and go back and look at the register file examples, can you spot the problem? So can you initialize a register with a 16-bit value? Well, the answer is kind of no. If you could get the 16-bit value into memory, then you could use a load instruction. So you could read the 16 bits from memory and load it into a register. But how do you get that value into memory in the first place? If you're looking to load a register with an immediate value, then we're constrained to an 8-bit immediate value within our instruction. And as you can see here, we can load 8-bit values into the register because they're loading in an 8-bit value and then sign extending or padding out with a 0. But we can't load a true 16-bit value with the instructions we've got at the moment. You may think that's a fundamental design flaw, but it's quite a common problem in most machines because you have a disconnect between the size of your instructions and the size of your data, as we saw in the simple CPU version 1A, where we had a 16-bit instruction and 8-bit data. We have the same problems with this processor. Again, we could solve this by increasing the size of the instruction, allowing us to define 16-bit immediate values, but that would increase the size of our instruction memory, which is always a finite resource. So what you find in most machines is that we implement this functionality using multiple instructions rather than defining one instruction to do this particular task. And that's not so much of a disadvantage because you tend to only initialize these registers with these larger values infrequently. So if it takes a few more instructions every now and again, that's not a great performance hit. Okay, a quick quiz to test your understanding of RTL syntax. Can you use these instructions to load a register with the value AAAA? As always, you may want to pause the video here and work through this one as the answers follow. So just to go through these instructions, these use standard RTL syntax. So you can see here we're updating register RA with the concatenation of the sign bit and the lower 8 bits stored in the instruction register. So this specifies the low byte concatenated with bit 7 of the instruction register, so the sign bit of that immediate value replicated 8 times. This is a shift left instruction, so whatever's in RA is shifted one position to the left and the void created is filled with a 0. And obviously bit 15 is lost because it's shifted it out of the register. And immediate bitwise OR, so again the immediate value stored in the instruction register is bitwise ORed with the value in RA, and as this is a logical operation, the high byte is padded with zeros. What we have is our program here, and in the comments we have the value that will be in register RA. So initially we have to load our desired high byte. That will be loaded into register RA, sign extended. So you can see here we've got the AA, and then because the most significant bit is 1, it'll be sign extended, so you get 1s in the high byte. And obviously we don't want that. So to move the AA into the high byte position 8 times, and you can see that's what we're doing here. So each time we implement a shift left, inserting a 0 function, the bit positions move to the left 1 bit position, and eventually we'll move the AA into that high byte. Finally, we perform the bitwise OR to load in the low byte to get our desired 16-bit value. But it does take 10 instructions, which is a little bit on the long side. So typically what you will find in most processors is that you'll have explicit move instructions or load instructions that rather than moving the immediate value to the low byte, as we have in this move instruction here, they move the immediate value into the high byte position, so you'd move it into the high byte position. So you have 2 different types of move instruction. So you'd have one that moves the immediate value into the low byte position and one that moves it into the high byte position. So using just 2 instructions, we can create our 16-bit value. Improvement number 3, addressing mode. So with the addition of our register file, multiple general purpose registers, we can now add some new addressing modes. We can add register addressing, where all operands are stored in registers, so not stored in memory or as immediate values, and register indirect, where we can use a register to store an address of where in external memory the data is stored. So we've got some examples at the top here. So we've got a register addressing mode add instruction. So now we're adding together two values stored in registers. So the value in RA is added to the value in RB, and we store the result in RA. We've got a register indirect load instruction. So the previous load instruction just had the external memory address, and it was implicit where the result would go, RA. But now, rather than storing the address as a hard-coded value, we can use one of our spare registers. So within an instruction, a register indirect addressing mode is shown by the round brackets. So whenever you see a round brackets, you know that this register contains an address that you'll be used to access external memory with. So for the load, RA, RB, so we use 12 bits from the 16-bit value stored in RB to put onto the address bus. We read memory using that address and store the result in register RA. Again, how do these new addressing modes affect the instruction formats? What bit fields do we need within these instructions? Do we need numbers within those instructions? Well, the answer is no. So for the register and register indirect addressing modes, everything's just stored in registers. So this frees up quite a lot of instruction. So we can see some examples. Here we've got a move instruction where we're moving the value stored in register RB into RA. So you can see here I can define these operands just using 4 bits. 2 bits for the destination register and a 2-bit for the source register. The lower 8 bits aren't needed, so what you typically find, we use these 3 bits to expand our opcode field, allowing us to define more instructions. So we indicate this in the simple CPU version 1D by having the opcode field set to all ones. When the processor sees that, it knows that these are register-based instructions, and therefore it will look at the lower 4 bits to see what type of register instruction it is. So a key advantage of these addressing modes are that they help reduce the size of your program. So now we've got the ability to store data on the processor within the 4 registers within our register file. We need to store less variables out in external memory, so therefore we'll need less load and store instructions. So significantly helping improve processing performance if we can store frequently used variables in these registers. Also removes the need for self-modifying code. So now I have register indirect addressing mode for my loads and stores. I can use a register as a pointer into memory. I don't need to modify the address stored in the instruction as I had to do in the simple CPU version 1A. I can just update a register. Again, adding functionality always comes with a hardware cost, so we do need to make some modifications to the processor. So for the simple CPU version 1D, that means the addition of some more multiplexers to route the various register values around the processor. So you can see here for the register indirect, we use that lower multiplexer from our register file to route the address up to the address multiplexer so we can read that value from memory. We also need to add an additional input to our data multiplexer so that we can route back to register values when we're performing a register addition, for example. So we'd route one operand value using the lower multiplexer as we did for the register indirect through here into the ALU, and the other one through this top path to the ALU. Again, increasing hardware and possibly increasing the critical path delay, which will obviously slow down our system clock speed. Another consideration is what type of instructions are we going to support in our processor? Should all instructions be able to use these different addressing modes, or should it be limited to particular instructions? Also, should we use 2 or 3 operand formats, and should we use other addressing modes to improve the functionality of a processor? So there's a few examples here. So another common addressing mode is displacement addressing. So here you can see where, okay, I've got a register indirect, so I'm using a register to store an address, but in displacement addressing mode, but we add on an offset, a displacement, which is stored as an immediate value within the instruction. So this value here, so this 8-bit value here. So when you read memory, you read the address specified by the register, but plus an offset. And obviously that would require an additional adder within our processor. Also, we could include 2 or 3 operand format instructions. So you can see here we've got an add instruction where we just got 2 operands. So we're reusing one of the bit fields to specify the source and destination. So in this example, the RX. So you can see we're adding RX to RY and updating RX. But if you want to improve the flexibility of your instructions, you may want to specify each source and destination. So you can see here in the 3 operand format, we can define the destination and the sources separately. And obviously all that adds hardware complexity to our system. Again, all of these are choices for the designer and are very much dependent on what application domain the processor is working in. Our fourth improvement 4, the support for subroutines. So we have been using macros in previous labs to help minimize the amount of code that we need to write, and if used correctly, macros are a very powerful programming technique, especially if you can harness the power of recursion, but that is a tricky programming technique. The downside of macros is they don't improve our code density. They don't help reduce the size of our programs, as they just cut and paste in code. So to help us implement functions within our program, we need to use subroutines. So a subroutine is a write once, use many times programming structure. So to give some examples of what we have been doing with macros with the simple CPU1A processor, here's some macros. And we can see how we can use a macro to implement a bitwise OR instruction. So as always, within a macro, we define the macro's name and the text we want it to be replaced with, but we can also implement some pre-processing to modify the parameters passed to our instructions. So the first two examples here implement simple register clearing and setting. So we can clear the simple CPU version 1A's accumulator by setting it to 0 or setting it to all ones. The bitwise OR one is here, so OR the accumulator, and that's implemented using a bitwise AND and a add instruction. So what we do is we use the eval function as part of the M4 preprocessor we are using, and it modifies the parameter we pass to the OR macro. It performs the inversion of that parameter by excluding ORing it with the value 255 before runtime. So if you look at the example here, so if we pass the macro the value AA, that will be passed as $1 here. Exclusive ORed with 255 will obviously invert all the bit positions, so AA gets converted to 55 hexadecimal. So when the processor executes this instruction at runtime, it will clear the bit positions that we want to set, and then when we add the original parameter passed back to it, it will set those bit positions. So if that was a bit confusion, let's have a look at the program here. So we can see this is our program. We implemented it on the simple CPU version 1A. So we clear the accumulator, perform the bitwise OR with AA, so we should get AA in the accumulator. Then we overwrite it with the value F, and then perform the bitwise OR with again the value AA. So if you step through the code as it is executed, you'll see the value in the accumulator change as shown here. So initially we clear the accumulator, then we perform the bitwise AND with 55. Well, as it was all zeros, nothing changes, and then we add AA to it to complete our bitwise OR instruction. Now to show that one where the starting value wasn't 0, we move in F into the accumulator, implement the bitwise AND with 55. Obviously that will 0 the high nibble, and it will set 2 bits in the low nibble to 0, converting the F into a 5, such that when we add the value AA to it, it will restore the low nibble back to the original F and set the high nibble to the value A. Now macros are very useful when you're programming, as they can combine commonly used instructions into a single macro, helping to reduce the amount of code you have to write, but obviously those macros will be expanded into the machine code the machine runs, so you don't actually improve your memory efficiency. To allow us to do that, we need a subroutine. And what a subroutine is just a function that we can call multiple times from anywhere in the program. So we write the piece of code that we want to implement. So maybe, for example, that is a piece of code that performs the multiplication of two numbers, because obviously we can't do that directly in the processor. So we may want to call that multiplication function multiple times. So that's what this is showing here. So in the program, we've got these lighter blue bars here. That's when I want to call that multiplication program. So we will jump to the subroutine, perform the multiplication algorithm or the parameter we've passed to it, and then return back to the main program to the instruction underneath the call. And then we continue with the program, and then we can call it again, and then jump back to a different position. So the thing to note here is that we always jump to the same start address, the start of our subroutine, but we'll return back to the main program at different spots. And that's the functionality we now have to implement with two instructions, two special instructions, the call and return instructions. So these are implemented on the simple CPU version 1D as shown here. So the call instruction is pretty much the same format as an unconditional jump. So you have an opcode and then a 12-bit address where you'll be jumping to. But the key thing here is that when I do a call instruction, it makes a copy of the program counter so that the processor knows where to jump back to. And that's described here in this RTL description. So when I execute a call instruction, I push onto a stack the current program counter +1, so the return address I want to return back to in my main program. I then increment the stack pointer so I can call another subroutine if I want to, so a subroutine that calls another subroutine. And then I update the program counter with the address of the subroutine that I want to jump to. I then execute the subroutine, maybe a multiply function, and when I've finished I want to return back to the main program, and that's where I would execute the return instruction. And this is a good example of a zero operand instruction because obviously I don't have to pass it any parameters. It knows the return address is on top of the stack. So if you look at the RTL for the return instruction, you can see I decrement the stack pointer to point to the last address pushed onto the stack, and I pop it off and load it into the program counter and continue my fetch decode execute cycles. Now, to implement that on the simple CPU version 1D, I've modified the program counter to include a LIFO, a last in first out buffer. Now, this is slightly different to what you'd normally see in a typical processor, but I thought it'd be interesting to see how we could do this in hardware. We will be looking at the more traditional call return stack in the next lecture. So what we have is we have our 12-bit register, that is our program counter. So we pass that program counter to a adder to add one to it to generate the return address, the address of the instruction underneath the call instruction, pass that to our LIFO buffer. Now inside here we have this circuit. So we have 4 registers, a 2-bit counter, a 2 to 4 1-hot decoder, and a 4-input multiplexer. And this will implement our stack, and obviously it's limited to a depth of 4 because we've only got 4 storage locations within it. So before we talk through how this circuit operates, what does this circuit here do? So quick quiz. Can you tell me what this one does? As always, you may want to pause the video here as the answer follows. So if you look at this truth table, A and B are inputs, Y and X are the outputs. So do you take A and B as being a 2-bit value, so 0, 1, 2 and 3, you can see the output here has been decremented by 1. So if we start here with 1, obviously 1 goes to 0, 2 goes to 1, 3 goes to 2, and obviously 0 would go to -1, and as a 2's complemented value, that will be obviously 1, 1. So going back to our circuit diagram here, this counter here implements our stack pointer. So obviously that's a 2-bit stack pointer, and that is passed to the decoder. So initially that will be 0, so this will be giving 0, enabling the top one. Every time I push a value onto the stack, this counter will be incremented by 1, enabling the next register within that stack. To read off the values, obviously I need to decrement that stack pointer, and that's what our decrementing circuit does do. So if the current stack pointer is the value 1, this register will be enabled to allow me to push a new value on, but when I want to pop the value off, I want to read the value stored in the first register, and that is selected using this decrementer here to select that top input. To see how that circuit will work in action, we can go through these nested subroutine calls. So in this example here, we can see how our main program can call a subroutine that calls a subroutine that calls a subroutine that calls a subroutine to do some processing. So when the processor is reset, the 2-bit counter will be reset to the value 0, so that will be our write pointer, and the output from our decrementer is the read pointer, so obviously 0 minus 1 will be 3. So we execute the first call instruction, and we want to jump to subroutine A. So we push onto the stack the return address, so if this is address 0, the return address will be 1, so we push into the first register the value 1. We then increment the stack pointer to point to the next free location, so the 2-bit counter goes to the value 1 and the decrementer goes to the value 0. We then update the program counter with the address of subroutine A and jump to that instruction. At that location we have another call instruction. We have a call instruction that calls subroutine B. So we push onto the stack the address of the instruction after that call instruction. So that'll be address 0, 1, 2, 3. So you'll see that goes to the value 3. We then increment the stack pointer to point to the next free location on the stack, and obviously the decrementer will follow. We then update the program counter to the address of subroutine B. At that location we have a call to subroutine C. So again we will push onto the stack return address of where we want to go to, which will be this address here, so 0, 1, 2, 3, 4, 5, and put that into our stack. Then as always we increment the stack pointer to point to the next free location, and the read pointer follows, and then we update the program counter to the address of subroutine C. At subroutine C we have another call instruction to subroutine D. So again we push onto the stack the return address, so obviously that's address 7, and then we increment the stack pointer, which wraps around to address 0, and the read pointer then obviously follows. And then we update the program counter with the address of subroutine D. At this stage our call return stack is full, so if we were to call another subroutine it would corrupt the data that is stored on here already because we've reached our maximum depth of 4. So in this last subroutine we do some processing, and then we execute the return instruction. So the return instruction will pop off the stack the return address pointed to by the read pointer, our decrementing circuit. So that is address 7, so that will take us back up to this return address. We decrement the stack pointer to point to the next free location, which obviously will be address 3, and the read pointer obviously follows. So now we execute the next return instruction, so we read off the return address, so that'll be address 5. We update the program counter, which takes us to this return instruction, and obviously again we decrement the stack pointer to point to the next free location in our stack, so address 2. Again, the return instruction is executed, which will pop off the return address 3, which will take us to this return address. Again, we decrement the stack pointer to point to the next free location on the stack, so that's address 1 now. And we execute the return instruction, which pulls off the stack the final return address, which gets you back to the start program, and the whole thing repeats again. Now, there's lots of different ways of implementing this core return stack. The LIFO implementation we've seen here is typically used in smaller processors. So if you look at the Xilinx Picoblaze processor, for example, you'll find a comparable implementation there. Alternatively, in other processors, when the call instruction is executed, the program counter is automatically saved into a general purpose register. Then it's the responsibility of the software running on the process to store that return address in a software controlled stack. Alternatively, you can have this process automated with some additional hardware control, and the return address is automatically written to external memory. And now we'll be looking at one of these implementations in the next lecture. We'll also be seeing how we can use an external stack to simplify the process of passing parameters and returning results to our program. Okay, to finish off a summary, so we expanded the capabilities of the simple CPU processor. We've added more memory. You always need more memory, and we've increased different addressing modes to help improve the processing performance, so register addressing, register indirect. And we've seen how we can improve our memory efficiency, the code density, by using subroutines, writing a function once and reusing it, rather than using macros which would just cut and paste the same code multiple times within our program. When we design a processor, we've got some choice to make. Do we go for an orthogonal instruction set? Do we allow each instruction to use each addressing mode? Or do we put limits on it to simplify the hardware? That's very much a compromise to be made, depending upon the application domain of your processor and how much processing performance you need. Okay, I think that's where I'll leave it there, and we'll continue this in lecture 6b.